Hello everyone, this is Joshua Foreman, and I'm here to present the findings of my Physics 22-12 Lab 5 on a bar magnet. So the key physics principles at play that we're going to discuss that go into this lab is, first of all, the magnetic dipole field, which is the field pattern that is contributed by a bar magnet, which follows this formula below. We can notice how it simplifies very well when mu and r are parallel, rather where they're either parallel or perpendicular, because the dot product very much simplifies when something's parallel or when something's perpendicular, which follows the parallel and perpendicular formulas that we're already aware of. Another physics principle that we need to be aware of is the superposition, that the net magnetic field contributed by the bar magnet is added to the magnetic field contributed by the Earth to get the net magnetic field that the magnetometer reads. So it basically just states that magnetic field is additive when you're contributing from different sources. So some assumptions going into this lab are that only the Earth and the bar magnet are contributing measurable fields to the magnetometer. We're also very much assuming that the magnetometer works, which I wasn't entirely sure if it does. And so the experiment involves first finding the magnetometer and then placing it certain distances parallel to the bar magnet and then certain distances perpendicular to the bar magnet, and recording the magnetic field at these distances, as well as the magnetic field at a 45-degree angle from the bar magnet. So here's the data we charted. The data has a general trend line sloping at -2, which I'm a bit confused about because the formula above right here says that it should be -3 because it changes with r cubed, which means that if it's inversely proportional to r cubed, then the natural logarithm should be, then taking the natural logs on both sides, we should expect the slope to be -3. Here's the code that goes along with the data. The code very much turns this into a mathematical, computational simulation model using the formulas that we know and plotting the arrows based on this at certain distances. We get a nice diagram up here. And so now what if we double the magnets? So if we were to double the magnets, then, well, if we were to stack the magnets back to back, then the fields contributed by them would point in the same direction. And so we're essentially doubling the magnetic field without changing the direction. And so the mu, the magnetic dipole moment, would double, which means that in general, all the numbers should double. At least I think. I can't imagine it being any other way. And lastly, what if we didn't rotate our phones to account for Earth's magnetic field? Well, we're trying to show how the magnetic field recorded on our phone differs with distance from the bar magnet. And distance from the bar magnet does not affect the Earth's magnetic field, because we're still on Earth no matter where we move our phone relative to the magnet or how much we rotate it. And so the Earth's magnetic field should be the same in terms of which direction it's pointing, maybe not with respect to the phone, but it should still contribute the same amount, which means that we have a large variable in here that doesn't change with respect to distance cubed, which means that we would not get a nice trend line, but rather something more confusing. And what went wrong with our lab? I was told that doing the tape, it should be on the left side, I believe, and it was on the right side of the phone, or it was some other thing. It was either that or the other way around. So also the compass was acting a little wonky, so maybe it is supposed to be -3, or maybe it's supposed to be -2, and I'm just missing something about this formula. Maybe the mu and the r cancel out in some way to assure that it actually is an r squared type relationship. But anyway, I hope you enjoyed this video. and I hope that you're having a wonderful spring break right now.